So looking at the big ideas in logs and exponents, the idea is just make sure that you understand how the base and the base are related, the argument and the answer here to the exponent is related, and the log equals the exponent, right? There's our x. And there's three parts to this. There's whether it's in log form or exponent form, there's three parts. There's a base, argument, exponent. And how are those things related in their context? So again, just remember that logs and exponents are the same thing. They're just different ways to write the same thing. And what happens in a log, right, since they are equivalent expressions, something must be happening in exponent and vice versa. And when we look at a log expression and it's really complicated and difficult, we might want to just switch it to an exponential expression and we can deal with it in an exponential form. Okay, and there's no big deal in doing that because essentially logs and exponents are the same thing. So the thing that we're going to focus on is that if we change one part of a log or exponent, that change shows up in another part. So for example, if I square this side of the equation, well, I know that I must square this side of the equation. So changing the argument here, right, how does that affect my log? Well, it changes my log there. Okay, so there's these relationships, and I'll go over that one again, but there's different changes that we can see that happen in logs and happen in exponents. And for the most part, we're probably more familiar with exponents. So I'm going to show the reasoning behind some of the changes in logs based on exponents. So here are basic rules. Okay, so so just so that you understand how this is set up, the blue represents the argument, the green represents the base, and the red represents an exponent. Okay, whether it's in log form or in exponent form. Okay, so the z is this small z is the power on base a that gives me big Z. The small x, the power on base a that gives me big X. Okay, so if I have some number z times x, I can add the exponent powers when these bases are the same. Same thing here, z and x share the same base. So if I divide these arguments, okay, I can subtract the exponents on that base. Okay, whatever common base we're going to use between those two numbers. And if I have an exponent external to the argument x, I can apply that exponent as a multiplier on x. Right? And the equivalents are shown in log form here. So this equivalent shows up as multiplying the arguments, we add the exponents, dividing the arguments, we subtract the exponents. If I have power to power, okay, I multiply the powers together, or I can bring that power to the front. Okay, so it multiplies the log, okay, because log equals the power. So how do these things show up? Well, we can, if I have this basic definition, a to the power x equals our big X, a to the power z equals big Z. Well, when I have our x times z, okay, that's if I have my arguments multiplied, well, that means that x is going to be my a base with power, where's my green here? So it's going to be a to the power x, so I'm going to bring that x to the outside there, okay, times, where's my a here? So times a to the power z, okay, so the z then comes on the outside there, so basically I have this a in the base there. Okay. Now again, we can justify lots of changes in this. Okay, so here's my a. So let's say I power my a like this. I power it by 2. Okay, what has to happen on the other side to balance it? Okay, I've got to power that by 2. So if I power 2 here, I've got to power 2 here. Okay, so that's an equivalent change. Okay, if I power that by 2, okay, so that's a change. Let's say I can just move some things around, right? So let's say there's a power there. Well, this could be grouped into here, right, as a times 2. Well, this power 2 then should be able to be moved to power 2 here. And these are equivalent changes because that power 2 went from here to here, right? From power 2 to there. And really, if you look at the exponential, yeah, that's perfectly okay to move that power from here to here. So in the log form, there's an equivalent, okay? So there's this idea, there's this equivalent changes that we can see in exponents and logs. So I'll show you one other thing here. So let's say I have a power and I want to undo this power by square rooting. Well, what has to happen on this side? I've got to square root that as well. Okay, so if I square root here, I have to square root here. Okay, so there's something that can show up. If I undo that power by square rooting, okay, so I had a power here, so I square root, square root. So if I want to get rid of that power here, okay, I can square root there like that. Okay, so there's an equivalent again. Let's say I had a power here, so there's my power, and I want to, what I could do is I could always undo this power by getting rid of it by dividing the power like that. So then that means that if I get rid of this, I can divide like that. Okay, those are equivalents. Okay, that now I wouldn't necessarily do that because that's, you know, not the easiest way to keep track of things, but I can, those changes are possible. And again, it's just starting to get the idea of how these things are connected to each other. Essentially, they're connected through equations. What we do to one side can show up on the other side. So here, if I have an exponent, and where my exponent here, let's say that's exponent x, if I power the base and the argument the same, yeah, it doesn't affect my exponent whatsoever. This change here and this change here balances each other off. So really that just can show up in this way too, that I can power the base and the argument the same. And this is what we kind of looked at in the other one, that other property we looked at that I was showing on the other video. But it can also show up as power here on the argument and as 2 on the x. So this is equivalent here.